Okay.
Okay.
Two ways to do this problem. Let's take the most obvious way. It may not be what she wants, but both of them are going to give you the same answer. Okay?
Mm-hmm.
Let's figure out the average rate of change over the time period. In other words, how has it changed? Excuse me, I forgot to click on the screenshot here. How has it changed between 1978 and 2014, the last year we have data on? How many years have taken place, and what is the time change?
It's like 14 seconds less.
If you subtract 824 minus 811, you get 13.
13.
And that's actually 13, are those seconds?
I don't know.
I don't know either, and I don't know that it matters. We'll
Okay.
call them seconds. In other words, it's a long race. It's 8 hours or 8 minutes and 24 seconds. Okay, so there's a difference of 13 seconds over how many years?
2016.
Subtract those two dates.
38.
Here's the way I do it. How many years between 1978 and 2000? Well, that's 22, right?
Yeah.
And then how many years between 2000 and 2014? That's 14. 36 years. So it's that. So that's the average rate of change, which is the slope of the linear line that you would draw if you were graphing it. In other words,
Okay.
because she says use a linear model, then we can take this average rate of change, which is like a third. Let's get that. Do you have a calculator? Do you have a calculator? What is 13 divided by 36?
Okay, 13 divided by 36.
Mm-hmm.
0.36.
Okay, so we're shaving off 0.36 seconds per year. Right? Does that make sense?
Yeah.
We've gone from 824 to 811 in a period of 36 years. Now, why did I put the 13 in the numerator and the 36 in the denominator? Is because I want my answer to be in seconds per year, right?
Mm-hmm.
So, what's the 2016 prediction going to be? Remember, we're losing, we're shaving off that much per year.
So, would I do 811 minus 0.36?
Now that's per year.
So
I'm going 2 years from 2014 to 2016. So I'm going to lose this much, 72 hundredths, or excuse me, 72 seconds. 0.72 seconds. Sorry. So this time is going to be 8 minutes and 10 seconds, approximately. I'm rounding everything off, but I'm gonna shave off almost a whole second. Okay, Now, let me just, this really actually does end up mattering whether we're talking minutes or seconds here. Let me see what, they don't tell you even. Well, I know that an 800 meter does not take 8 hours to swim. So that's got to be 8 minutes and 24 seconds. Okay? And it's not 8.24 minutes either. They wouldn't have a colon there. There would just be a period. So we're definitely going to read that 8 minutes and 24 seconds. So we're losing a third of a second approximately per year. So we're only going to shave off 2/3 of a second in 2 years. So this is, be lucky if we get it down to 8:10. Now, which begs the question as to why did she say the lucky guess, the actual time was 8:04? Well, it shows you the problem with statistics. In other words, she said stud because she did an 8:04 in 2016, and just based on the normal progression of the times based on years, it should have only been 8:10. So she must really be special, Katie Ledecky. She's not only breaking the linear pattern, she's by a lot. Okay? Now, that's one way to do it. The way they probably want you to do it is to lay out an XY grid. This is going to be time on the horizontal axis. Excuse me. Let me label that again. I meant time, but I don't want to label it with time because that says time. That's what that is the vertical axis is the time axis. And what the horizontal axis is years since 1978. Okay? So, the very first point we have, which is at 0 years since 1978, should be a time of 8:24. It's the very first time we have. Well, at 9 years, it goes down to 8:22. So let's see, we have how many years here in total? 36. Let's make that 9. So 9 years after 1978, the time has dropped to 8:22. And we can see that this is going to be a line with a negative slope. Well, the next point they have is 1989, which is the 11-year point. And that is at 8:16. And we begin to see that it does look linear. And if we plot all of these out, now I go through a 17-year jump. In other words, I go to year 30 is my next data point, 2008, and I'm only down to 8:14. Now it's beginning to look not so linear. Starting to look a little curvature in that. I go 5 years out, which is 35 years since 1978. And I've only lowered it by 1 second over 5 years. And that is 8 minutes, 13 seconds. And finally, by the 36th year out, it's been lowered to 8:11. Okay? Now, so that's our data plotted. And when they say use a linear model, they mean run the best line you can through those data points. Well, I can almost run a straight line. That's not a bad straight line. It's supposed to be a straight line, but that's not a bad representation of what's happened, right?
Mm-hmm.
Well, guess what the slope of that is? The slope of that line is our negative 0.36. And notice this is in seconds, and this is in years. So it's negative 0.36 seconds per year.
Why is it negative?
Because the slope of that line is negative. It's cutting the times as we go, as we progress from 1978 to current times, the time has decreased.
Okay, that makes sense.
That's a negative slope. And it should be negative. We are shaving time off. So, what would a linear equation of this thing look like? In other words, I wanted to put it into the form y equals mx plus b, which would then allow me to make predictions about future years. What would m be?
The negative 0.36?
Yep. X is the number of years since 1978. And what would B be?
The 0.72?
The y-intercept. That's what B is the y-intercept. 8.8 minutes, 24 seconds.
Okay.
And I'm going to write it like that. In other words, you could convert it to a decimal. In other words, 24 seconds is not quite a half of a minute. So that might go to 8.4 minutes. And I really should do that. In other words, you can't mix numbers and hours and minutes representations. You should convert this. What's 24 divided by 60? 4/10. That's 2/5. It's 40%. So let's write this as, instead of 8 minutes and 24 seconds, let's write it as 8.4 minutes. You with me?
Mm-hmm.
And you see where I got that? That's our starting point. And if you want to test that, put in an x of 0. In other words, when x is 0, it means we should have the time that was 1978. No time has passed since 1978. And if I put in an x of 0, I get y equals 8.4, which is the time that was set in 1978. 8 minutes and 24 seconds is 8.4 minutes. Now we have a linear equation that predicts this model. And they want to know what the time, the record-setting time, should have been based on this linear equation for the 2016. So here's how I would do it. I would say y is equal to 0.36, and x in this case is 38 years, right? In other words, 2016 is 38 years after 1978. So I'm going to put 38 years plus 8.4, and that's a negative, excuse me. And that's what will give me the predicted record-setting time in 2016. And doing it the other way, we got about 8 minutes and 10 seconds. Okay, so that's what it would have been by this model. In actuality, Katie did it in 8 minutes and 4 seconds. So her data point would have been way down here. She would have lowered it by that much. We'll call that 8 minutes and 4 seconds. So that's what this page is all about. I don't know of any other way to express this. Now, I'm a little puzzled by something. What is that and why is it there? I see what it is. It's the difference between...
I don't know. I wrote that.
What's that?
I just wrote that. I was just
Okay,
writing how
well,
much.
that's not bad. Yeah, I mean, that's one way to investigate this relationship. Unfortunately, this doesn't give you a lot of information. The first method I did where I found the average rate of change was based on a 36-year period from 1978 to 2014. We had data between those 2 years. So I can definitely say that over that 36-year period, the time dropped by 13 seconds. So that's definitely 13 seconds divided by 36 years. And that came out to be 0.36 seconds per year. Negative because it's dropping. If the time was going up, it'd be a positive slope. But the times are dropping. So with this equation that I've circled over here on the right, you could say, what will the times be in the year 2020? Where X would be 42. And you just fill it in and you'd get a prediction. And wouldn't be that much. In other words, I can tell you right now, it would be based on this model, it would be like 8 minutes and 9 seconds. So it's going to be a while before this model ever predicts 8 minutes and 4 seconds. Katie Ledecky's record may stand for some number of years, unless some, once in a generation swimmer comes along and breaks it. But based strictly on the way the world record has dropped over a 36-year period, she was extremely unusual, almost an outlier. Tiger Woods-esque. That dominant, okay? Yeah, these differences between the times that you've put here, this 2 and 8 and so forth like that, that would allow you to calculate the average rate of change between 78 and 87. And it would allow you to calculate the average rate of change between 87 and 89. But then you'd have a bunch of average rate of changes that would all be a little different. And the more reliable statistic is the average rate of change for the entire 36-year period between 1978 and 2014. That's the most reliable number. Is the more data you can get, which is to say 36 years rather than 9 years, the better off you're going to be. Notice that first 9 years, it did not drop an average of 0.36 seconds per year. In 9 years, it only dropped by 2 seconds. So that's like 0.2 seconds per year dropping. So it's not terribly consistent, but if you use the entire 36-year period, you get a nice semi-straight line.
Okay.
All right. What else, Haley? You want to go back and look at some of the material we didn't cover last time? I think that's it on this page, is it not?
Yeah.
Yeah.
There's we started a new unit, and it's solving for substitution and then linear combination methods.
Okay. I can do a few of those just to take up the last 10 minutes. Let's do that. Let's pick them up. What they're teaching you is how to solve a system of equations. If I had 3x plus 4y equals 12, and I also told you that y was equal to 2x, can you solve that system of equations? And there's two primary methods that they're going to teach you. One is substitution, the other is elimination. Correct? Have they taught those to you yet?
Yeah.
Okay. Whenever one of the two equations is fully solved for one variable, like this one, you want to use substitution.
Okay.
Okay. So what can I write? If I want to substitute this into the first equation, then my first equation is going to look like this. 3x, what's the rest of it?
Plus 2x?
No, plus 4 times 2x.
No.
What I'm doing is whenever I run into a y, I'm substituting 2x because this one tells me y is equal to 2x.
Okay.
Okay? And that's still it. Now I have one equation and one unknown and I can solve it. I get 11x equals 12. X has to be 12 elevenths. And y is twice x, so y has to be 24 elevenths. That's substitution. Okay? Now, let's say that they didn't give you the second equation in that format. Here, let me erase everything. It's easier than trying to erase it. So here's the first equation. This time I'm going to make up a different second equation. Okay? The second equation is going to say 2x minus 4y is equal to 13. Two completely independent, separate equations, same variable, this x equals this x, this y equals that y. And because we have two equations, we can now solve this. If you only have one equation and two unknowns, you have an infinite number of solutions. But if you have two equations and two unknowns, generally you can solve it. Not always. Sometimes they'll give you tricky combinations where there won't be a solution or else there's still an infinite number of solutions. But the key is having two equations that are different. Okay? Now, notice my second equation is not solved for a variable. I don't have it y equals something. I don't have it x equals something. This is standard format where the x and the y are on the left side and the numbers on the right side. That's also standard format, equation number 1. When both your equations are in standard format, it usually is much simpler to solve it by elimination. And you can always add equations or subtract equations. You can't multiply them, but you can add them and subtract them. What happens if I add these two equations? What do I get?
A 5x?
Notice what gets eliminated, the y.
Mm-hmm.
In other words, it's plus 0y, so I'm not going to write it. I added the left side, so I got to add the right side.
25.
Now x has to be equal to 5. And once I've solved for x, I can go back into whatever I feel is the easiest equation and solve for y. Well, that equation looks a little easier to me. It doesn't have any negative signs in it. So I substitute my x value that I solved for right there and then solve the equation for y, and I'll have an answer for y. Well, if I take that down over here where I have a little bit more writing room, I get 15 plus 4y equals 12. 4y equals minus 3. Y equals minus 3/4. There's my y answer. And you always have to solve for both x and y.
Okay.
In other words, it's not enough to just solve for the first variable. And usually when you're using elimination to solve two systems, a system of two equations, it's a little harder in solving for the second variable. As you noticed, I had to go back in and substitute into one of these equations and then do more algebra to solve for y. Whereas in the first case, where we used substitution, solving for y was a lot easier because it was equal to 2x. So it was pretty simple. But here, not as simple to solve for the second variable, but more simple to solve for the first variable. In other words, by elimination, you get it down to one variable immediately. Now, these can get harder. This is probably one of the simpler cases that I could give you, where all I had to do was add the two equations and one of the variables disappeared. It isn't always that easy. There are, here, let me give you one more. And this time my second equation is going to be this. Okay? Now notice that whether I add the two equations or subtract them, I don't eliminate a variable. So I have to manipulate the equation first. I am allowed to multiply any equation by the same amount on the left as the right, okay? So I'm going to multiply the left side by 2 and the right side by 2. That gives me a new equation 2 that now says 4x minus 4y equals 20. That's my old equation 2, but notice my new equation 2 is the same as the old equation. It just now has a minus 4y, which means I can eliminate y. By adding these things together, I get 7x equals 32. There's my answer for x, 32 divided by 7. So sometimes you have to do some algebra in order to, and sometimes you have to multiply both equations by different numbers in order to get like a common denominator almost. The whole idea is to get those two equations to a point where you can eliminate a variable by adding the two equations together.
Okay.
Okay. All right, that's a good place to stop. That should give you a little bit of a more understanding of the section you've just started. Those are definitely the two primary methods. The third one is graphing. You graph one, you graph the other. Wherever they cross, that's the solution.
Okay.
Those are the three methods that you're going to have to know how to do. Okay?
Okay.
All right, Haley. I will talk to you next time. Have a good rest of your week.
You too.
Bye.
Bye.